In this clip, we're going to talk about place value. And what we mean by place value is that in our enumeration system, which we call the base 10 system, the value of a digit, it depends on its place within the number. So for example, with this number that we would read 4,642, the same symbol is used twice, namely the number 4. It is used here and here. Place value, though, tells us that the value of this 4 is different than the value of this 4. We read this number in terms of expanded form, 4 thousands plus 600s plus 4 tenths plus 2 ones. So this 4 is in the tens place, it represents 4 tens or 40. This 4 is in the thousands place, it represents 4 thousands or 4,000. Again, we would refer to this as the expanded form of the number 4,642. An expanded form is going to come up later in many contexts as well. Okay, so in our base 10 system, our kind of governing rule is that 10 of any one place value denomination is equivalent to 1 of the next higher denomination. And to motivate how we count and how we'll end up doing arithmetic in our base 10 enumeration system, we can think of the following example. So suppose someone came into this room and dumped a giant pile of sticks on the ground and asked you to count them. Now, one way to do this would just be to count individually. 1, 2, 3, and so on and so forth. Let's say you get up to 642, 643, 644, and so on and so on. And if someone comes into the room and interrupts you, then if you happen to lose your train of thought, you're in trouble, right? Because you're going to have to go all the way back to the beginning and start over again. However, there might be a more efficient way of counting. Suppose, for example, anytime we got to 10 sticks, we took a piece of string and we wrapped up 10 sticks and made one what we are going to call tens bundle. And let's say we just do this with all the sticks on the ground as long as we can. So anytime we get 10 sticks, we wrap them up and we call that a tens bundle. So when we're done with that, we're going to have a bunch of tens bundles lying on the ground and then possibly some individual sticks lying on the ground as well. Well, after we're done with that, we can continue. We can take 10 of the tens and wrap those up with a bigger piece of string and call that a 100s bundle. And we can keep doing that until we're finished, and so on and so on. And when we're done with this entire process, we're going to have a bunch of bundles of sticks lying on the ground. We're going to have individual sticks, which we could call ones bundles. We're going to have those tens bundles that are bundles of 10 sticks wrapped together. We're going to have hundreds bundles, which are essentially 100 sticks wrapped together in the form of 10 tens bundles, and we could also have thousands bundles and 10,000s bundles and so on and so forth. Hopefully we wouldn't have that many sticks to begin with. The point is that that exercise can tell us what our individual place value denominations are. If we combine that exercise with this rule of the base 10 system, then we get our individual place values. So again, we could have had some individual ones bundle sticks lying on the ground. What that tells us is that our smallest place value, at least when we're dealing with whole numbers, is going to be the ones place. The place value one higher than that, we can find either by our counting sticks example or simply by our rule of the base 10 system, which says that 10 of one denomination makes 1 of the next higher denomination. If our first denomination is the ones place, since 10 ones is equal to 110, then our next denomination is going to be the tens place, and so on and so forth. Since 10 tens is equivalent to 1 100, our next place value would be the hundreds place. 10 hundreds is 1 1000, the next value would be the thousands place, and so on. And we can use as many place values as are needed. How many ever sticks are on the ground, we can use more and more place values to record that number. Incidentally, this idea can tell us how to figure out what decimal place values are. A mistake that a lot of students make when they're first learning about decimals is they're looking for a pattern, so they see ones, tens, hundreds, thousands, and they think mistakenly that the first place value to the right of the decimal point has to be something called the ones place, whatever that would mean, simply because of the symmetry in the language. But if we think about it according to our rule of base 10, that 10 of one denomination makes 1 of the next denomination, we can figure out what the first denomination would be past the decimal point, right? 10 of whatever this denomination is going to make 1 of this denomination, which is the ones. And once we learn a little fraction arithmetic, we will realize that 10 tenths is equivalent to the number 1. And therefore, this place is the tens place. And just like we did to the left of the decimal point, we can continue on to the right of the decimal point as much as needed. Okay, so we see that our system of recording decimal numbers, or numbers that are numbers with decimal points, is just an extension of this place value system, this base 10 system that we learn very on in elementary school. Now, place value is a vitally important concept in early elementary grades because, as we're going to see a little bit later, it forms much of the foundation of the arithmetic algorithms, the addition, subtraction algorithm, multiplication, and division algorithm as well. On the other hand, place value can be very tricky to teach simply because it is a very subtle idea, and as adults, we have been dealing with this idea for our entire lives, and we really haven't been thinking about it. It's just common knowledge to us that, again, in this number 4,642, that this 4 represents 40 and this 4 represents 4,000. We don't even think twice about it. But for a student seeing this for the first time, it can be difficult to get their head around. So for that reason, we often use models at an early age to re-emphasize some of these concepts. We discussed in our introductory clip that the Singapore approach is based on the following model: concrete, pictorial, abstract. So in early grades, often we use concrete manipulatives, for example, to emphasize certain concepts. And with place value, that's done through base 10 blocks. Then we move on in maybe later grades to kind of pictorial representations of these concrete ideas we were using in earlier grades. And then finally, since the power of mathematics is really in its abstract nature, we move on to the abstract concepts in later elementary, middle school, and high school grades. So if we were, in the place value context, thinking of base 10 blocks as kind of the concrete example, then if we move to the next level of pictorial representations, we can use something that's used in the Singapore text called chip models. So a chip model is a really nice way to represent numbers, and it also is going to give us a way to illustrate and motivate the addition and subtraction algorithms, as we're going to see in the next clip. So right now, I'll just give you an example of a chip model, and then the next clip we'll see how they're used to illustrate the algorithms. Now, as teachers, we understand what the kind of models are going to be used for. The models are, the great power in these models is the fact that, again, they're going to parallel the steps that are used in the addition and subtraction algorithm. So we want to keep that in mind when we introduce the models at the beginning. Because at the beginning, models are simply used to record numbers. So, for example, let's say we simply wanted to record the number. Let's just use the number we've been using. 4,642. Let's say we just wanted to record this number on a model. Now again, you can imagine what you would be doing if you had base 10 blocks. You would have different size blocks, ones blocks, tens blocks, hundreds blocks, and thousands blocks, and you would have 2 ones, 4 tens, 6 hundreds, and 4 thousands. All we're going to do with the chip model is we're going to kind of translate that onto a picture. So we have a model, a rectangular model, and you'll notice that we keep the columns nice and neat because we know as teachers that when our students learn the addition and subtraction algorithms, being neat is really important, right? Stacking our numbers up really neatly in columns is really important to be able to successfully navigate the algorithms. We're going to label each of our columns with the necessary place values. In this case, we need 4. So we've got a thousands place, a hundreds place, a tens place, and a ones place. And again, all we're going to do is just kind of, again, it's a pictorial representation of expanded form. We've got 4 thousands, 6 hundreds, 4 tens, and 2 ones, and we're simply going to record the number of chips that we need in each place value. By the way, in the Singapore textbooks, these chips in the thousands place will actually have the number 1,000 written on them. In the hundreds place, they'll actually have the number 100 written on them. In the tens place, they'll have little tens written on them. In the ones place, ones written on them. I obviously can't do that here. You'll have to use your imagination. But again, this is how we record numbers. And again, all we're going to do is just kind of, it's a pictorial representation of expanded form. We've got 4 thousands, 6 hundreds, 4 tens, and 2 ones, and we're simply going to record the number of chips that we need in each place value. In the Singapore textbooks, these chips in the thousands place will actually have the number 1,000 written on them. In the hundreds place, they'll actually have the number 100 written on them. In the ones place, ones written on them. I obviously can't do that here. You'll have to use your imagination. But again, this is how we record numbers, and what we're going to do next in the next clip is use these models to motivate the steps of the addition and the subtraction algorithm.